Now I'd like to talk about something called the Arrhenius equation. And the Arrhenius equation looks at the rate constant, that's a little k, and its dependence upon temperature. And so we have temperature up here. So this is the Arrhenius equation. You can see that it's got an exponential function of the activation energy, E sub A, and since the universal gas constant is going to be in units of joules per mole Kelvin, then our activation energy has to be in joules too, and oftentimes it's given to us in kilojoules per mole. So similar to delta H reaction, and because typically they are in the 20 to 50 to 100 kilojoules per mole. But make sure you take care of the units there. Now breaking this down, so A is what's called the Arrhenius pre-exponential or frequency factor. It is usually a very large number, and it accounts for the frequency of collisions that have the correct orientation to react. And we're not going to say a whole lot about that other than we can determine it when we do plots, and so we will know, or graphs, and that there are a large number of collisions, and then there's the exponential factor here, and it accounts for the fraction of collisions that have enough energy to react. So what we will see is there's a very large number of collisions and a much smaller number that actually have enough energy to react. This has to do with the Boltzmann distribution. And if you remember the Boltzmann distribution, the y-axis was the fraction of molecules, and the x-axis, at least for one of them, was the kinetic energy. And it looks something like this. And what we're saying is that as temperature increases, or let's say this, so at some point there's a set of collisions that have enough kinetic energy to react, and as temperature increases, that number of collisions increases exponentially, and that's what happens. That's what this term means, and that's what it says right here. So it's true. Now let's get into taking this and how we use it. We will linearize the Arrhenius equation, and in order to do a linearization, again, where we're going with this is what kind of plot can you use to determine the activation energy. So we're going to take the so we have an exponential term here, we're going to take the natural logarithm of both sides. So let's see, there's my rate constant, A e to the minus EA over RT. So we will take the natural log of both sides. When we do that, on the left-hand side, we will have the natural logarithm of the rate constant, and then we'll do this nice and slowly here. So we've just distributed that natural logarithm. Then we can see that there are two terms that are multiplied together on the right-hand side. Those two terms, when they're multiplied inside the natural logarithm or the regular logarithm, then they are added. Next, the exponential and the natural logarithm terms cancel each other out. So we still get ln of A, we get minus EA over R, and I'm going to break it up here into two parts because we are now done. We will write out our equation for a line. Y equals mx plus b, where I've put the b over here because b is our y-intercept, and the natural logarithm of a, the frequency or collision factor, let's say the Arrhenius pre-exponential factor, is going to be our y-intercept if we plot the natural logarithm of the rate constant versus 1 over temperature. So natural logarithm of the rate constant versus 1 over temperature, where our units have to be in 1 over Kelvin. And if we do that, then the slope is minus EA over R. That's an A, not a 9. I apologize there. And it will be in a straight line. It will have a negative slope. It'll look something like this when we plot it. And slope equals minus EA over R. Multiply the slope times R and take away the minus sign, and you will get the activation energy. Okay. Now, as we've done before, we can turn that into what's called the two-point slope formula. And that's the version that is on your conversion and equation sheet, and that you are more likely to need for the exam. So here's an example. It says the activation energy for the reaction blah, 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 blah is 186 kilojoules per mole. If the value of the rate constant is given here at 322 degrees Celsius, what is the value of K at 50 degrees Celsius? And the two-point slope formula, so we have two different temperatures. We have one of our K values. The only thing we don't have is our other K value. Let's go ahead and plug things in here. So natural logarithm, we don't have K2, that's what we're going to be solving for. K1 is 6.76 times 10 to the minus 4th seconds to the minus 1 equals minus EA, so that's going to be 186,000 joules per mole over R, 8.314 joules per mole Kelvin. And then 1 over, let's see, T1 is going to be 322 degrees Celsius. I get 595 Kelvin and 50, 323 Kelvin. We can see that our joules per mole cancel here. Our Kelvin, so this is in the denominator of the denominator, so it kicks it back up top, which means it will cancel with our Kelvin over here. And now we've plugged everything in. Let's go ahead and solve this. I'm going to do this term first. So 323, 1 over, minus 595, 1 over. I get for this term 1.415 times 10 to the minus 3. Then I'm going to multiply that times 186,000 with a negative. Divided by 8.314. I get this whole term is minus 31.66. And that's going to equal the natural logarithm of K2 over 6.76 times 10 to the minus 4th. And whatever units I have on the left-hand side in this natural logarithm, seconds to the minus 1, will stay the same. So my answer will be in seconds to the minus 1. Let's see. I think what I need to do actually is plug in or take the exponential of both sides. That's going to be e to the minus 31.66 And for that, I get 1.8. So let's see. So now these two cancel. I'll be left with K2 over 6.76 times 10 to the minus 4th equals 1.8 times 10 to the minus 14. Multiply these two to find K2. And I'll just use 1.8 there. 1.8 exponents. So exponent 14 minus times 6.76 exponent 4 minus. I get 1.2. I think that was 1.80. So I'll keep my 3 sig figs as normal. I did keep an extra one up there, but I always end up with 3. 1.22 times 10 to the minus 17. Yes. Good. Just making sure I actually worked that out correctly with my notes. And now let's do a second problem. It says it's a companion problem, but I'd like to work it. For this particular one, it says the activation energy of a first order reaction is 50.2 kilojoules per mole at 25 degrees Celsius. At what temperature will the rate constant double? And this is a problem where we are going to again use the 2-point formula, and it's going to go natural logarithm K2 over K1 equals minus EA over R 1 over T2 minus 1 over T1, and that's a 2 there, sorry about that. And what we're going to do is, so it's a pretty general question. We know our activation energy, good. We know our temperature 1, good. And we don't have a value for either K1 or K2. And so what I'm going to do is I'm going to assume K sub 1 equals 1. That means that K sub 2 equals 2 because it doubles. That's all it means. And so now I have both of these. I have R. The only thing I don't have is T2. And so just K2 divided by K1 will just be 2. So natural logarithm of 2 equals, plugging in all my numbers, converting this to joules, it's going to be 50,200 joules per mole over 8.314 joules per mole Kelvin, 1 over T2 minus 1 over T1 in Kelvin, 298 Kelvin. And so the only thing we don't know is T2. Let's go ahead and solve for it. And I just sort of work this out as I go. So I've got 2 natural logarithm is 0.693. Do this math here. 50,200 divided by 8.314. And I get 6,038, which is negative 1 over T2 minus, now I'm going to go ahead and do this math, 298, 1 over 3.356 times 10 to the minus 3rd, like so. I know it's not fun math, but let's go ahead and keep working it out. So divide both sides by 6,038, negative, I guess. And I get 0.693 divided by 6,038. I get minus 1.148 times 10 to the minus 4 equals 1 over T2 minus 3.356 times 10 to the minus 3. So I do get a little nervous with these small numbers, so that's why I've kept an extra sig fig. And we're doing subtraction here. So I will end up getting back to 3 sig figs for my final answer, but I want to make sure that not too much cancels out here when I do the subtraction. Let's see. So far, so good. Now I'm going to add. And so I'll just do this minus that. 3.356 exponent 3 minus 1.148 exponent 4 minus. I get that 3.241 times 10 to the minus 3 equals 1 over T2. Then I can reciprocate that, and I'll just leave it like it is this time. Living dangerously, right? And then I will, so I'll write that 2 down there, not that dangerously. And then I will do 1 over. And my temperature turns out to be 3 sig figs T2 equals 309 Kelvin, which equals in degrees Celsius minus 273. I get 36 degrees Celsius. And so this is a useful thing to think about. That's why I wanted to work this companion problem. And here's why. So this 50.2 kilojoules, that is a typical activation energy for a biological process. So a typical activation energy for a biological process. And if we think about a biological process, we could think back to when I was talking about that tuna sandwich that I left in my car. And so let's see, from 25 to 36, so every approximately 10 degrees Celsius, every increase in temperature of approximately 10 degrees Celsius doubles the rate of reaction, doubles the rate of bacteria formation. If you've got a fever, you don't want to get 10 degrees over your body temp, but it does. So that temperature we think of as you have a fever and it only goes up a couple degrees, it is increasing your reaction rates, but not double. But my tuna sandwich, if it went up 30 or 40 degrees, that's double. That's 8 to 16 times faster bacteria growth. But to complete this thought, typical activation energy for a biological process, every increase in temperature of approximately 10 degrees Celsius, that's the difference between 36 and 25, doubles the rate of bacteria growth. And of course, it's just doubling the reaction rate, and it's a little abstract, but that is a general rule of thumb for bacterial processes. And of course, it's much more complicated than that, but chemistry can contribute to our understanding of bacteria growth.